Hey everybody, my name is Ryan. Today we're going to be deriving the heat diffusion equation in Cartesian coordinates. So the first step in deriving the heat diffusion equation in our Cartesian coordinate system is going to be drawing out a differential control volume in that coordinate system. So since we are dealing with the Cartesian coordinate system, the differential control volume is going to take the shape of a cube. So this cube is infinitely small and has side lengths of a differential change in position in each of our dimensions. So for the Cartesian coordinate system, this is going to be dx, dy, and dz. Excuse me. So these are going to be the side lengths of our cube. Now, Fourier's law states that the heat flux in a given direction, which is represented symbolically by a q sub x, and I'll use the x dimension as this example. So the heat flux in the x direction, q sub x with two apostrophes, is equal to the negative thermal conductivity of the material times the gradient of temperature in the direction that we're working with. So q sub x with two apostrophes, negative k dt dx, symbolically. Now again, this is a heat flux, so this means that this is a heat flow per unit volume. Now Fourier's law is great, but by itself it doesn't really allow us to calculate temperature profiles or analyze how temperature changes within a medium with time. So to go from Fourier's law to the heat diffusion equation in Cartesian coordinates, we will need to perform an energy balance. Now Fourier's law will come in handy a little bit later on in this derivation. So I'm going to write it up top and we will come back to it a little bit later. So to perform our energy balance, the first thing that I'm going to add to the visual depiction of our differential control volume are heat flows coming into the control volume. So those are going to be represented by Qx, Qy, and Qz. I'll go ahead and add those right now. So Qx is going to be the heat flow coming into our differential control volume in the x direction at some position x. So again, this is going to be Qx. We're also going to have Qy coming in from the bottom. And then Qz is going to be coming into the control volume in the z direction. So this is going to be going kind of up and to the right, just basically representing going into the cube, into the board that we're working with here. So again, Qx, Qy, and Qz are going to be heat flows coming into the system at a specific position, x, y, or z in that direction. Now, if we have heat flows coming into the system, we will also have heat flows coming out of the system. So I will add those as well. So these are going to be represented by q sub x plus dx coming out of our differential control volume in the x direction. So this expression represents the heat flow coming out of the differential control volume at some position x plus some differential change in position x dx. And again, dx is going to be our width in one dimension of our cube, which is a differential control volume in the Cartesian coordinate system. Now, one of these are heat flows, not heat fluxes. So in Fourier's law, we were dealing with heat flux, which is going to be a heat flow per unit volume. These are flows, not fluxes, because they don't have that double apostrophe on them. That'll come in handy a little bit later on in our derivation. So again, we have Qx coming in, heat flow coming into the system, Qx plus dx, heat flow coming out of the system at some differential change in position, dx. Now, I will add those for the other dimensions as well. So out the top of our cube, we have Qy plus dy. And going out the back of our cube into the board, we have Qz plus dz. And again, just to summarize, these are heat flows coming into our differential control volume in each of the three dimensions. And then heat flows coming out of our differential control volume in those same three dimensions as well, x, y, and z. Now, there are two other terms that are going to be going on inside of our differential control volume, and these are going to be our energy generation, our heat generation term. So it's going to be E sub g with a dot, and then we're going to have our storage term, energy storage term, E sub st with a dot. Now we will explain these in just a little bit, but first I'm going to write out very simply, very broadly, our overall energy balance for, excuse me, our differential control volume. So we're going to have all the way up at the top here, energy in plus energy generated equals, or excuse me, minus energy out is equal to energy stored. Now, before we get into these other two, our EG dot and EST dot, our generation and storage terms, we're going to write this out and kind of explain it as we go. So I'll rearrange this so that we have the in minus the out terms. So our energy flow in, and this dot represents the rate, so the rate at which that energy flow into the differential control volume changes with respect to time. We're simply going to have Qx plus Qy plus Qz, and those are our heat flows coming into the differential control volume in each of those dimensions, x, y, and z. Minus our heat flows out, which, as we said earlier, are just going to be Qx plus dx plus Qy plus dy plus Qz plus dz. Now, this whole thing is going to be subtracted from our energy flow in. So again, this is our energy in, rate of energy flow into the differential control volume, minus our energy out. So next we have to add our energy generation term. And again, the dot represents that this is a rate, the rate at which the energy generation inside our control volume changes with respect to time. So in general, energy generated within the system is going to be thermal energy generated. So that could be from any number of sources, a chemical reaction occurring inside of the medium that we're analyzing, electric or conductive heating that's going on, like in a chemical reactor. When concrete is curing, it releases a lot of heat. That could be another example, some kind of radiation going on. We're going to leave this just as an energy generation term, however, but again, it could be from any number of sources. So to represent this in our energy balance, we're going to leave this as Q dot. Now, Q dot is going to be our energy, our thermal energy generation, our heat generation per unit volume, so specific energy generation, times that unit volume, which is going to be our the volume of our differential control volume, dx times dy times dz. So again, our generation term is going to be Q dot times dx dy dz. So this takes care of the left side of our energy balance. I'm going to go ahead and draw an equal sign. We're going to do the right side, which leaves our energy storage term. Now again, the dot represents that this is a rate, so energy, the rate at which the energy storage inside of our system changes with respect to time. So in this case, the energy that is stored inside of our differential control volume as we're analyzing it is going to be represented by a change of temperature of the medium that we're dealing with. So the change in temperature of the fluid, of the solid, whatever medium we are, the energy that's stored inside of the system is going to be taking the form of thermal energy as a change in temperature of the overall medium that we're dealing with. So, excuse me, the first factor that we're going to use to represent this is going to be our specific heat capacity, which represents how much heat in the system is being absorbed per unit mass. Now, when we're looking at the heat diffusion equation in the Cartesian coordinate system, we're dealing with how heat flows, how heat changes with respect to a space. So how heat is changing with respect to a differential change in position. So the specific heat capacity represents the heat that's being absorbed in the system per unit mass. So we're also going to multiply this by the density of our medium to connect this mass back to a volume, because that's going to agree with the rest of our equations here that are dealing with the differential control volume, dx, dy, and dz. Now, these two are constants for a specific medium. So the next term that we're going to add is a change in temperature with respect to time. Now, again, this is how the energy is going to be stored in our differential control volume. If thermal energy is being stored inside of this control volume, the temperature is going to increase. So that's why we have our change in temperature with respect to time, because again, this is a rate. That dot is what represents the rate. So change in temperature with respect to time. Now, lastly, we will also multiply this by our unit volume, which is going to be our control volume, dx, dy, and dz, to form an overall energy storage rate term. So I'll put a box around this, and we're going to go through some different manipulations and some simplifications, but I will put a box around this because this is our overall energy balance at this point in time. Now, the first simplification, before we get started, I'll take another sip of water. The first manipulation of this that we're going to do is going to be something called a Taylor series expansion. And I'm going to perform this Taylor series expansion using the x dimension as an example, and then I will apply that to our energy balance and rewrite it in just a few moments. So a Taylor series expansion. Now we're going to use the Taylor series expansion to rewrite our energy flow out terms. So again, qx plus dx, the energy flow, the heat flow that is leaving the system at some position x plus some differential change in position x dx. So the Taylor series expansion allows us to rewrite this, so qx plus dx, heat flow out, as our heat flow in qx plus the sensitivity of our heat flow with respect to a change in x. So that's dqx over dx differential. But again, this is the sensitivity of that heat flow with respect to a minute change in position dx times the actual change in position dx, which again is the width of our differential control volume dx. So again, this is the Taylor series expansion, which just allows us to simplify, or to rewrite our heat flow out of the control volume in each of our dimensions. And again, we're using x as an example here. So if we were to take our energy balance and rearrange this and group together our x terms and our y terms and our z terms, I'll draw the x terms here, we would have heat in, qx, minus heat out. And if we rewrite our heat out term, heat flow out using our Taylor series expansion, we have qx plus sensitivity of that heat flow with respect to a change in x times the actual change in x dx. So this is going to be our heat flow in minus our heat flow out. Now, if you notice, qx occurs in both of these with a minus sign, so these are going to cancel. So this term can be rewritten simply as the negative sensitivity of the heat flow in the x direction with respect to x times the differential change in position x. So if we apply this Taylor series expansion to all of our dimensions, x, y, and z, we can rewrite our energy balance as follows. So for each of our dimensions, x, y, and z, we're going to have the negative sensitivity of that heat flow in that direction times the change in the differential change in position in that direction as well. So I have that for each of our dimensions, x, y, and z. Plus our generation term that we dealt with earlier, q dot times our differential control volume, dx, dy, dz. And again, q dot represents the heat generation inside our control volume per unit volume. Is going to be equal to our heat storage term, energy storage term, density, specific heat capacity, differential change in time, or change in temperature with respect to time, times our control volume, dx, dy, dz. So I'll put a box around this because, again, this is our modified energy balance. A little bit messy, and I hope you can see this, but the next modification, simplification, manipulation that we're going to do on our energy balance is going to take us back to Fourier's law. So I'll go ahead and rewrite that here. So the Fourier's law states that the heat flux, which is represented by Q sub x, and x is the direction we're dealing with two apostrophes, the heat flux, which is the heat flow divided by unit area, is equal to the negative thermal conductivity of your material times the gradient of temperature in that direction. So as we mentioned before, the heat flows in and out of our system that we're dealing with, qx, qy, qz, and then those heat flows out, adding some difference in position. These are heat flows, not heat fluxes. However, we can use Fourier's law to rewrite these to incorporate that cross-sectional area through which that heat is flowing. So again, if we use x as our example, we can rewrite the heat flow in the x direction, q sub x, as the heat flux in the x direction times the cross-sectional area, which is going to be negative thermal conductivity, area, and then that change in temperature with respect to the x direction. So if we're looking at the heat flow coming into our control volume in the x direction, the cross-sectional area through which that is flowing is going to be this area of this face here on the right and on the left of our cube. So the dimensions of that square, that cross-sectional area, are going to be dy times dz. So we can then go ahead and rewrite this heat flow, Qx, as negative K, thermal conductivity, times dy dz, then that change in temperature with respect to the x direction. Again, this is an application of Fourier's law, and I forgot to write that here, but Fourier's law allows us to rewrite this flow in terms of our thermal conductivity, cross-sectional area, and then change in temperature with respect to a change in the x direction. Now, if we take each of these terms from our energy balance, again, I'll use x as an example here, we can rewrite this using this Fourier's law expansion. So if we take this term, we have the series expansion, but if we sub in the heat flow expansion from Fourier's law into this expression, we then get that same differential equation that looks something like this. So inside of that derivative, we have negative thermal conductivity, dy, dz, and the change in our temperature with respect to the x direction. On the outside, we have that dx as well. So because we're taking a derivative with respect, partial derivative that is with respect to the x direction, dy and dz do not depend on x. So these can actually come out of that derivative. And we have, and then also our negative signs are going to cancel. So in a simplified manner or a rearranged manner, we have the partial derivative with respect to the x direction of our thermal conductivity times the derivative of temperature, partial derivative of temperature with respect to a change in x position. On the outside, we now have dx, dy, and dz. Now this should look a little bit familiar because this is the differential control volume that we also see in the expressions for our heat or energy generation term inside of our control volume, and also the energy storage term. And that's actually going to be the last step of our derivation here, is dividing out that differential control. Lost the cap there. That is going to be the last step of our derivation, dividing out that differential control volume to ultimately get our heat diffusion equation, and we'll get there in just a second. So again, using the Taylor series expansion and Fourier's law, we can rearrange our heat flows to end up being here, and I will apply this to our energy balance and rewrite it as follows. So in each of our directions, each of our dimensions, that is, the x, y, and z dimensions of our Cartesian coordinate system, we're going to have the change with respect to x of our thermal conductivity times the change in temperature with respect to a change in the x position, or in that dimension, times our differential control volume, dx, dy, dz. So I'll repeat that for each of our dimensions, the other ones being y and z. We're almost running out of space here on the board. I think we'll be all right though. dx, dy, dz. So these represent the heat flows for all of our three dimensions. And then again, we can't forget about our heat generation term. So Q dot, heat generation per unit volume, times our unit volume, dx, dy, dz, equal to our heat storage density times specific heat capacity times differential change in temperature with respect to time times differential control volume, dx, dy, dz. I'll go ahead and put a box around this again because this is our energy balance with all of those modifications, manipulations that we've described above. Now again, as I mentioned before, you may notice that all of these different terms have our differential control volume, which is dx times dy times dz, which is the volume of our differential control volume, the Q, because we're in the Cartesian coordinate system. So our final step will be to divide dx, dy, and dz out of each of these terms, and that will leave us with the heat diffusion equation, which I'll write out right now. So after we divide out the differential control volume, for each of our dimensions, we simply have the quantity of the thermal conductivity times the differential change in temperature with respect to x, and then the change of that entire quantity with respect to x. Repeat that for the y and z dimensions. Add those up, plus the specific heat generation term, Q dot, which is just the heat generation in our system per unit volume, is equal to the heat generation term, or excuse me, the heat storage term, density times specific heat capacity times the differential change in temperature with respect to time. And this leaves us with the simplified general form of the heat diffusion equation for Cartesian coordinates. Thank you. All right, so for this portion of the video, we're going to be deriving the same heat diffusion equation, but in spherical coordinates this time instead of Cartesian coordinates. So the first step to deriving the heat diffusion equation in spherical coordinates is understanding where the spherical system fits into the Cartesian system and how they relate to one another. So I'll begin by drawing out a Cartesian system of coordinates here. We've got x, y, and z. And then the first dimension in the spherical system of coordinates is going to be the r dimension, the radial dimension. So we're going to draw this r ray coming out from the origin here. We're going to drop down a normal line to the y plane and then connect it back to the origin as well. So the angle that is formed between the vertical y direction, the vertical y-axis, and this radial axis here, this is going to be called theta, and this is our azimuthal angle. And this angle down here that is formed between this projection of the r ray and the z-axis on here, this is going to be the phi angle, the phi direction, and this is going to be our polar direction. So these three coordinates, the r, phi, and theta, are going to make up our spherical system of coordinates for our heat diffusion equation. Now, similar to the previous derivation, the first step in deriving this equation is drawing out our differential control volume. Now, this is going to look kind of like a cube, but it really is just a spherical section with infinitely small side lengths and area and volume. This is going to be the differential control volume for the spherical system of coordinates. Now, these rays here kind of connect imaginarily down to the center of our sphere. And again, it looks kind of like a cube, but it's a spherical section. So beginning with the r direction, this width here is going to be simply dr. Now looking at the theta direction, this angle here, or excuse me, this distance here on this part of our control volume is going to be the radius of that ray times the angle, which is going to be d theta, that infinitely small section of that angle theta. So this angle here is going to be r d theta, or this side length, excuse me, is going to be r d theta. Now lastly, in the phi direction, this side length here is going to be r sine theta d phi, because the length of this projection here on the y plane is going to be r sine theta, and then multiplying it by the difference in the angle phi is going to be the r sine theta d phi. Now again, just like in the previous derivation, we start with Fourier's law. I'm going to draw this up here because it is a little bit tight of a board, so just want to make sure we keep enough space for the rest of the derivation. But again, we begin with Fourier's law. Now Fourier's law states that the heat flux in a given direction, we'll use R as the first example here, is equivalent to the negative thermal conductivity times the temperature gradient in that same direction. So symbolically, we have QR with two apostrophes for the heat flux is equal to negative K, the thermal conductivity, times differential dt over the R, which is going to be the temperature gradient in the R direction. Now, if we look at the units for this, the units of flux are in watts per meters squared, because flux is flow divided by cross-sectional area. Now, the units for the temperature gradient are going to be Kelvin, units of temperature, times distance, just in meters, which leaves the units for our K to be Kelvin over watts over meters Kelvin, just so everything cancels out nice and easy. Now, if we look at the phi direction next, we've got Q sub phi these two apostrophes, the heat flux in the phi direction, equal to negative k over dt over d phi. Now, it might be easy, might be simple to assume that this is going to be the correct form of Fourier's law, just because it looks very similar to the radial direction. However, this isn't correct. If we look at the units for the temperature gradient in the phi direction, we would get Kelvin over radians instead of Kelvin over meters. So radians, radial distance, but not a linear distance. We need this to be a linear distance. So instead of having simply dt over d phi, we're going to rewrite this as dt over r sine theta d phi. Now, adding in this r sine theta in the denominator allows us to analyze the change in temperature with respect to the actual distance that's being traveled by that flow as it flows through our differential control volume. And that also allows the units to work out, so we have Kelvin over meters. Now, similarly, our last dimension, the theta direction, our flux is going to be q sub theta with two apostrophes equal to the negative thermal conductivity dt over r d theta, just again so that we are traveling that full distance through our control volume and making sure our units agree with one another for Fourier's law. Now, Fourier's law by itself does not allow us to calculate any temperature profiles or changes in temperature over time. So we'll leave this here for right now, but it will come back into play later on in our derivation. So the next step is going to be performing an overall energy balance for our differential control volume in spherical coordinates. So we will begin by our heat flows coming into the differential control volume in all three of our dimensions, r, phi, and theta. So beginning, we have qr coming in this way. We're going to have q theta coming up through the bottom. Then we're going to have q phi coming into the page, kind of into the board, going back this way. Now, these terms, again, are heat flows, not heat fluxes. So these will just be in terms of watts, and these are equivalent to the flux multiplied by the cross-sectional area. And again, that'll come back into play later on in the derivation. So QR, for example, represents the heat flow at some specific point in space R as it is coming into the differential control volume. Now, again, just like last time in the Cartesian derivation, if we have heat flows coming in, we also have heat flows coming out. So with the R direction again, coming out, we have QR plus DR, which is that same heat flow, but coming out, and including some difference in space, DR. Now coming out the top, we will have Q theta plus D theta in that subscript as well, which just represents some minute change in the azimuthal angle there. And then lastly, coming out the back, we will also have Q phi plus D phi, again, taking into account some change in that polar angle phi. Now, the two other terms that are going to be inside of our control volume begins with E dot sub G and E dot sub ST. Now, E dot sub G represents the rate at which heat is generated inside of our system. And similarly, E sub ST with the dot represents the rate at which thermal energy is stored inside of our system. So before we get into those, we'll write out our overall energy balance. So we have energy into the system minus energy out of the system plus energy generated inside of the system, or the differential control volume, is equal, lastly, to the energy stored inside of the system. So to write this out in simple terms, our energy flow into the system is going to be equal to QR plus Q phi plus Q theta. Our energy out is just going to be equal to the summation of these three heat flow out terms. So we're going to have Q phi plus D phi plus QR plus DR, writing these out of order, but we're going to have Q theta plus D theta. Now, these are added together, and then the whole thing is subtracted from our heat flows in. Now, next up, we have our generation term. So our heat generation inside of the control volume could be from any number of different sources. They could be from an exothermic reaction that's occurring inside of our control volume. Could be from electric or conductive heating inside of a reactor, but we will leave this just as a simple generation term. So we're going to represent this in our energy balance with a Q dot. Now, the Q dot is simply the rate at which that energy is that thermal energy is being generated inside of our system per unit volume. So we're going to multiply this by our unit volume, which if we multiply up the side lengths of our differential control volume here, we get r squared sine theta dr d phi d theta. So that takes care of the left side. On the right side, we have our energy storage term. So in this case, the way that the thermal energy in the system is going to be stored inside of our control volume is by a change in temperature. That's how we're going to represent how that energy is stored. So we'll begin with the specific heat capacity of the material that we're working with, but this is in terms of mass. So we will also multiply this by the density of the material to get this quantity back in terms of space, because with the heat diffusion equation, we're dealing with how heat flows in terms of space, in terms of a change in position. So we need that density term in there to get this quantity back in terms of a spatial position or volume. We're going to multiply this by the change in temperature with respect to time. Now really, this respect to time is over this entire quantity, but we can just keep this right here with temperature. And then we're going to multiply this again by the volume of our differential control volume, which is going to be r squared sine theta dr d phi d theta. Now I'm going to put a box around this just to make sure we stay organized. This is our overall energy balance for our differential control volume in the spherical coordinate system. Now, the first step in walking this energy balance to the heat diffusion equation in spherical coordinates is going to be applying a Taylor series expansion. So I'll begin in the r direction. So the excuse me, the Taylor series expansion allows us to expand these energy flow or heat flow out terms and write them in a slightly different way. So the Taylor series expansion allows us to expand this. QR plus dr is equal to QR. The QR is just the heat flow coming into the differential control volume right here, plus the sensitivity of that heat flow with respect to a differential change in position, dr, times the actual distance, the actual change, big dr. So this is the Taylor series expansion for the heat flow out of the differential control volume in the r direction. Now, if we look at our energy balance, we can rearrange these terms so that we pair up the r terms together. So if we do that, we have QR, the energy or the heat flow into the control volume in the r direction, minus the energy or the heat flow out of the system. Now we're going to plug in our differential or our Taylor series expansion here. So this represents the net heat flow in the system in the r direction. Now these two QRs are going to cancel, leaving us with simply negative of the sensitivity of the heat flow QR in the r direction times dr, the actual change in the r direction in our differential control volume. So for each of these pairs, QR and then QR in and then QR out, we can pair these up, apply the Taylor series expansion, and rewrite our energy balance as follows. So the negative sensitivity of the heat flow QR in the r direction with respect to r times dr. And then we'll do the same for the phi direction, sensitivity of the heat flow in the phi direction with respect to a change in the phi direction position times that change d phi. Lastly, minus change of the heat flow in the theta direction divided by d theta, change in the theta direction, times the actual change d theta. And then we will simply drop down our energy generation and our energy storage terms from our above energy balance. So again, for the generation, it is Q dot times r squared sine theta. So the the thermal energy generation term per unit volume times our unit volume of our differential control volume, r squared sine theta, dr d phi d theta, equal to our thermal energy storage term, which is going to be density times specific heat capacity, change in temperature with respect to time, times our differential control volume once again, r squared sine theta, dr d phi d theta. And I will box this once again. At this point, Fourier's law is going to come back into play. So again, beginning with the r direction, Fourier's law will allow us to rewrite these energy flows, these heat flows, QR, Q phi, and Q theta coming into our differential control volume. So QR, again, is the heat flow coming into the system in the r direction at some specific point in space, r. This is equivalent to the heat flux in the r direction. So it's the same term, just with the two apostrophes, times the cross-sectional area through which that heat is flowing. So we already solved for this heat flux using Fourier's law up above. So we will rewrite this simply as the negative thermal conductivity times that area times the change in temperature with respect to the r direction. Now, the cross-sectional area, the heat flux is flowing in the r direction, is going to be a combination of these dimensions. So if the r is coming this way, that cross-sectional area is going to be this square on the right and this on the left, which are going to be r d theta times r sine theta d phi. So that A is going to be, so we're going to do this again, plug in for A. So we're going to have r squared sine theta d phi d theta. And then carry this term over, the change in temperature gradient in the r direction. So we'll do this the same for the phi direction, so Q phi is equal to the flux in the phi direction times that area. Now the area in the phi direction is going to be r d theta times dr. And then we have that temperature gradient in the phi direction. Now keep in mind, these two temperature gradients are going to look slightly different because we are accounting for that travel distance, not just change in the angle. So in the denominator there, we're going to have, for the phi direction, we're going to have r sine theta d phi. Once again, lastly, for the theta direction, we're going to have the flux in the theta direction, so Q theta with the two apostrophes for flux times the area equal to the heat flow in the theta direction. Negative thermal conductivity times the area times that temperature gradient in the phi or in the theta direction. So dt over r d theta. Let me write that as a partial. And if we rewrite this including that area, we are going to have the area that the flux is traveling through the differential control volume in the theta direction. We're going to have r sine theta dr d phi. R sine theta d phi times dr. And again, times that temperature gradient in that direction. So from the Fourier's law at the beginning, we have dt over r d theta. So I'll draw a line under here just to make sure that we can stay organized. So from here, we have used Fourier's law to rewrite our heat flows, QR, Q phi, and Q theta. So from this point, we can take these, plug them back into our energy balance, and then proceed with simplifying and deriving the heat diffusion equation in the spherical coordinate system. So beginning in the r direction, we have the negative derivative with respect to position r of our heat flow QR times dr. Again, this comes from the Taylor series expansion that we did just a few moments ago. So from here, we will continue and plug in our heat flow from Fourier's law. We've expanded that to include our, we've expanded that to include our thermal conductivity and our cross-sectional area. So I will go ahead and plug that in. Now from here, we can simplify this derivative a little bit. For one, these two negatives are going to cancel out. And also, since we're taking a derivative with respect to the r direction, sine theta, d phi, and d theta can all come out of the derivative. So dr here. So this can be rewritten as d over dr times, now the r squared does have to stay inside because we're taking a derivative with respect to r. Okay, dt over dr. Now on the outside, we're going to have sine squared. Excuse me, we're just going to have sine theta times dr d phi d theta. We'll proceed with the next dimension. So we'll start with, or continue with the phi direction. So again, we have our derivative with respect to position phi of our heat flow in the phi direction. And then we're going to plug in from our Fourier's law expansion. Caught a little mistake. I had a d theta in there instead of a d phi, or excuse me, instead of a dr. Let's see. Now we plug in q phi. All right, so again, if we simplify this derivative the same way we did above, we're going to have derivative with respect to the phi direction. And since we're taking a derivative with respect to phi, none of these depend on phi, so we can pull these all out of our derivative. So inside we only have the thermal conductivity times the temperature gradient with respect to the phi direction. Now outside, we're going to have 1 over sine theta times d phi, dr, d theta, dr, d phi, and d theta. Lastly, in the theta direction, we're going to have the negative derivative with respect to a position theta of our heat flow in the theta direction times d theta. And again, we're just going to plug in from our Fourier's law expansion. So we have the negative thermal conductivity times our cross-sectional area times the temperature gradient in the theta direction. And then we will simplify this derivative the same way as we have before. The negatives will cancel out. And then anything that is not in terms of theta will be able to be removed from the derivative. And the only thing that will remain inside are the thermal conductivity, of course, and also the sine theta term. We'll keep sine theta in there. Keep our thermal conductivity, and also our temperature gradient with respect to theta. And everything else on the outside will come out. So we have our r's are going to cancel out, sine's going to stay inside. We also have a d theta here. So which will leave on the outside simply dr, d phi, and d theta. Now from here, we have further manipulated our energy balance. So I will rewrite this, and I'll have to start over here because it's pretty long. And that will lead us to our final simplification of our heat diffusion equation in spherical coordinates. So here I've simply rewritten all of our heat flow terms from our previous energy balance. And notice that all of these include terms that are included in our differential volume, differential control volume. And then plus our Q dot, our heat generation term inside of our control volume with respect to with respect to volume times our differential control volume, r squared sine theta, dr, d phi, d theta. is equal to our thermal energy storage term, which is our density, times our specific heat capacity, times change in temperature with respect to time, times that control volume once more, r squared sine theta, dr, d phi, d theta. And we are almost there. If you notice, all of these terms include at least some of the parts that are included in our differential volume, r squared sine theta, dr, d phi, and d theta. So then our last step will be to simply divide out this differential volume from each of our terms, leaving us with the heat diffusion equation in spherical coordinates. All right, here we are with our final equation for the heat diffusion equation in spherical coordinates. So walking from left to right, we have heat flows in terms of R, our differential, or excuse me, the difference of the quantity R squared times our thermal conductivity times the temperature gradient in the R direction. That quantity, the difference in that quantity with respect to a change in R times 1 over R squared. Next, the partial derivative with respect to a change in position in the polar angle phi of K, the thermal conductivity, times the temperature gradient in the phi direction, times the quantity 1 over R squared sine squared theta. Lastly, in the phi direction, the partial derivative with respect to a change in the polar angle phi of sine theta times the thermal conductivity, and then the temperature gradient in the theta direction times 1 over R squared sine theta. All of those added together plus Q, which is our heat generation term inside of our differential control volume with respect to the unit volume, is equal to our heat storage term, our thermal energy storage term inside of our control volume, which is our density times our specific heat capacity of our material, and lastly, the partial derivative of temperature with respect to time. So here we are with the heat diffusion equation in spherical coordinates. Thank you.